So now we're going to start taking a look at how we can use some laws for calculating limits. So there's some things that we can know about limits that are going to be very easy for us. So if we've got a constant function, so say f of x equals c, then the limit as x approaches a of that constant function is just going to be that constant. So the idea here is, say we've got a graph where, let's say c equals 3. We just kind of have a nice horizontal line. Then no matter where we are or where we're trying to approach on the x-axis, the y value is always going to be whatever this c is. And so it'll just be whatever we're looking at. Now if we're looking at something where our function f of x is just equal to x, the limit as x approaches a of x is going to simply be a. So again, if we have this line y equals x that we're looking at, there are no weird things that are going to happen here. Any point that we look at for the value, the x value, will also be the y value, or the f of x value. So if we wanted to go ahead and compute these limits, say we were looking at something a little crazy, such as the limit as x approached negative 2 pi of negative 294, we'll notice here that there's no x term to really worry about. This is just a constant function. So here the limit will be negative 294. And if we looked at the limit as x approached 3 times e to the 7th power of x, well again, all we have is just x here, so it'll end up being 3e to the 7th. So we have some other laws that we can use to kind of come up with our limits. So let's assume for a second that both the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. So assume we can get those for whatever our functions are. If we're looking at the limit as x approaches a of f of x plus or minus g of x, then this is the same as the limit as x approaches a of f of x plus or minus, again depends, the limit as x approaches a of g of x. Alright, now let's say that k is some real number. If we've got some limit as x approaches a of that real number k times f of x, this will be the same thing as taking k times the limit as x approaches a of f of x. So just multiplying by a constant, we can basically ignore what we know about the limit. And so that'll be fairly simple. So again, using these laws, using the sum law, what we can see here is we can break up this limit. So if we wanted the limit as x approached negative 3 of x plus 17, this is the same as the limit as x approaches negative 3 of x plus the limit as x approaches negative 3 of 17. So we know based on our law earlier that if we're looking at the limit as x approaches negative 3 of x, that'll just be negative 3, and here 17 is a constant, and so we've got the limit as x approaches negative 3 of 17, so that'll just be plus 17, and so we will get 14 as our answer. Similarly here, we can go ahead and use the difference law to break this up into being the limit as x approaches 4 of 6x minus the limit as x approaches 4 of 5. Or we can break that down to be 6 times the limit as x approaches 4 of x minus the limit as x approaches 4 of 5. And so here we'll get 6 times 4 minus 5, or 24 minus 5, which is 19. Okay, so we've got some nice limit laws. We're getting some intuition built on how we can go ahead and break things down. We've got kind of these two fundamental building blocks up here. So we've got constants that we can take the limits of, and if we have just x, we can take the limit of that as well. And we know how to add these together and kind of pull out real number constants. But there are plenty more limit laws. So suppose again that we've got the limits for f and g existing as x approaches a, then if we're taking the limit as x approaches a of the product of those two functions being multiplied together, we can go ahead and separate them and find their limits separately and multiply those together. So if we know these limits, we can multiply them together. If we have the limit as x approaches a of f of x divided by g of x, what we can do is we can calculate those limits separately of each of those functions and then divide out those values. Of course, this assumes that the limit as x approaches a of g of x is not equal to 0, because again, we don't want to divide by 0. Then we have our power law. So assume that we're raising some function to some power. So say, for example, x squared. Then that's the same as finding the limit for our function and then later raising it to the power. So if we looked at, for example, the limit as x approaches a of x squared, well, this is going to be the same as the limit as x approaches a of x whole thing squared, which will just be a squared. So about what we would expect out of that. And then similarly with roots, if we've got the limit as x approaches a of the nth root of f of x, that's the same as the nth root of the limit as x approaches a of f of x, where here n has to be a positive integer. And again, we assume all the things we normally assume with roots. If n is even, then we have to assume that that limit is greater than or equal to 0. Alright, so let's kind of use these laws as a little bit of an example. So let's say we have the limit now as x approaches 2 of two different functions. For f of x, that limit is -5, and for g of x, that limit is 4. So we don't know the functions, but we do know what their limits are. So knowing this, if we want to compute the limit as x approaches 2 of f of x over g of x, then what we're doing is we're taking the limit as x approaches 2 of f of x and dividing it by the limit as x approaches 2 of g of x. And so we know both of these limits because they're given to us. So that gives us -5 divided by 4, -5/4. Similarly, let's say we wanted to go ahead and look at the limit as x approaches 2 of 2 times f of x plus g of x. Well, that means we can break this apart because there are two functions being added together, and we can pull the 2 out in front of the limit for this f of x. So we get 2 times the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. And so that gives us 2 times -5 plus 4, or just -6. Okay, let's do one more. So suppose this is what we have as our function breakdown, and we want to go ahead and split things up. Well, the first thing that we know is that we can divide this into a top limit and a bottom limit. So we have the limit as x approaches 2 of g of x minus 5 f of x, and maybe to help with this I'll put it all in brackets, divided by the limit as x approaches 2 of f of x squared. So then we can break that down even further using our limit laws. In the numerator, this will become the limit as x approaches 2 of g of x minus 5 times the limit as x approaches 2 of f of x. And in the denominator, what we'll have is the limit as x approaches 2 of f of x whole thing squared. Because remember, we have that law that says if we've got a function raised to a power, we can pull that power outside of the limit. And so breaking this down then, the limit for g of x is 4, minus 5 times the limit for f of x, which is negative 5, divided by the limit for f of x, which is negative 5 squared. Important to make sure that when you square this negative 5, you should get a positive 25. And so we'll have 4 minus negative 25, or 4 plus 25, divided by 25. So we'll get 29 over 25. So again, if you sometimes find yourself having issues with negatives, go through this process and plug this in your calculator, and you should be able to get the positive. So just a little bit of a good example to practice with those negatives. Alright, so I want you to take a moment and use the graphs of these functions. So this lighter one here is our g of x, and this upper one here is f of x, and see if you can find each of these limits. Alright, so let's say we wanted to find the limit as x approaches negative 2 of f of x plus 5 g of x. Well, we can break that down into being the limit as x approaches negative 2 of f of x plus 5 times the limit as x approaches negative 2 of g of x. So then, from there, what we want to do is we want to figure out what these limits are. So looking over at our graph, if we go to negative 2 on the x-axis, remember that our limit is not what our function value is. So here it looks as though we're approaching this 1, even though the function value is 2. We're approaching 1 as the limit there for f of x. So 1 plus 5 times, and then our limit for g of x as x approaches negative 2. And so this appears to be negative 1. So we have 1 plus 5 times negative 1, or just negative 4. Okay, so now let's say we wanted to go ahead and find the limit for as x approaches 3 of f of x over g of x. So this means that we then have the limit as x approaches 3 of f of x divided by the limit as x approaches 3 of g of x. So what we want to do is we want to be able to find both of these limits. So notice that f is not actually defined past 3. So we talked about the idea if we want to know what the limit is, we need to know what the limit on the left-hand side is and the right-hand side. However, there is no right-hand side to this. So even though it looks as though we have a value there, this limit does not exist. And so if this limit doesn't exist, then the whole thing won't exist. And so therefore we say that this one does not exist. Okay, and then last but not least, we want to go ahead and try breaking this apart. So this would be the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. Now when we look at the limit for f of x, it looks as though it's a 2. However, when we look at g of x, our left-hand and right-hand limits are not the same. And since our left and right-hand limits do not end up being the same, this limit right here does not exist, and so the whole limit does not exist. So again, we need to make sure we have our same limits on the left and right in order to be able to work with this. Now, something you may have noticed from some of our earlier examples is there are some times where we really could just go ahead and plug in a for x and go from there. So this leads us to the direct substitution property. So if f of x is a polynomial or a rational function, and we know that a is in the domain of f, then the limit as x approaches a of f of x is going to be f of a. So remember, polynomials are things where you have some power of x. So say ax to the, I don't know, 71st, this is just an example by the way, plus bx to the 70 plus, I don't know, we'll say cx to the 1 plus maybe some constant. And remember, these don't all have to necessarily be non-zero. So you basically have a bunch of these that you're adding up together, but they have integer exponents and they're decreasing. Or a rational function. So again, this is something where you have a polynomial divided by another polynomial. So as an example, if you had ax squared plus bx plus c over x cubed plus d, of where a, b, c, and d are all some sort of real numbers. So here, if you can go ahead and have a polynomial or a rational function, then typically your limit as x approaches a of f of x will just be f of a. So you'll just have to go ahead and plug in those values for a. So note that we talk about the domain of the function. So we talked about how rational functions have weird domains. You can't let your denominator be 0. So you won't be able to just do direct substitution when you're not on the domain anymore. And something else that we'll get into more in the next set of notes is that functions with the direct substitution property are called continuous at a. So we'll study more about what this means when we're in the next section. So note that when calculating limits, essentially we can try to start by just plugging in whatever number x is approaching. So that'll be kind of our starting point. And if we try to evaluate a limit using direct substitution and we get any indeterminate forms, then we have to go ahead and use some algebra to find the limit. So these indeterminate forms are basically things where we get 0 over 0 when we plug in, or we get something where we get infinity over infinity, or it could be negative infinities, or something where we have infinity minus infinity. So if we ever get any of these scenarios, what we're essentially saying is, well, we don't know yet what's going on, but we can do a little bit more work to find out. So first, let's go ahead and try to find the limit as x approaches 0 of x cubed plus 5x over x squared minus x. So this will be a way for us to try plugging it in. So if we plug in, what we'll get is 0 cubed plus 5 times 0 over 0 squared minus 0, which is going to be 0 over 0. So this is an indeterminate form. So what we should do is try some algebra. So one thing we can do is, if we want to try to get rid of any errors or issues we'll have, is we can go ahead and try to factor. So try factoring. So when we do this, what we'll get is this is the same thing as the limit as x approaches 0 of x times x squared plus 5 divided by x times x minus 1. And so when we do this, we'll see that the x's will cancel, and we'll get the limit as x approaches 0 of x squared plus 5 over x minus 1. So now that we've done a little bit of factoring, maybe now we can plug in. So now if we try to just plug in our 0, we'll get 0 squared plus 5 over 0 minus 1, or just negative 5. So that means that negative 5 is our limit for this function. Now notice that it's not something that you can actually plug in. So you can't plug in 0 to this function. But what this tells us is that when we're coming in from the left or from the right on the graph, we are approaching the value of negative 5 for our y values, so for our function values. Now sometimes we'll get something where when we go to try to plug in, we won't actually get an indeterminate. Now, if this happens, we'll get something where the limit does not exist. So say we wanted to go ahead and try this. So we tried to evaluate the limit of x cubed plus 5x over x squared minus x as x approaches 1. So what we'll do is we'll have 1 cubed plus 5 times 1 over 1 squared minus 1. And so then we get 6 over 0. So this is not an indeterminate form. So because we don't have 0 over 0, there's not some way for us to go ahead and cancel and reduce in a way that is true to what is going on with the function, and that will actually help us get to where we're going. And so because of this, because we have some sort of non-zero divided by 0, this tells us that the limit does not exist. And so in this case, because of this, we have a vertical asymptote. So this means we have a vertical asymptote at x equals 1. So before we were able to go ahead and compute our limit by taking our original function and replacing it with something that was a little simpler with the same limit. It worked there because the functions were the same except for where x equals 0, and when we were computing a limit as x approaches 0, we don't actually are considering what happens when it's equal to 0. So remember, we're not actually looking at the plugging in until we're at a point where we're ready to keep going with the limit. So I want you to take a moment and try evaluating these next 3 limits. The first one, I think you might be able to do on your own. The next 2 after that, give it your best shot with the algebra, but there's a good chance that you will need to kind of see the tricks that we can use. These tricks will be kind of standard things you'll use in your arsenal when you're trying to evaluate limits. So take a minute to try the first one and take a stab at the next 2, and then we'll go over them. Alright, so if we look at this first limit, so remember, we don't always have to use x. Sometimes you can use t. This time we're going to use h. It's just a letter. We're going to evaluate the limit as h approaches 0 of 3 plus h squared minus 9 divided by h. Now, I think we all understand that if we plug in 0 for h, we'll get a 0 in the denominator. But we should verify that we get 1 in the numerator as well, and so we get an indeterminate form. So what we'll get is 3 plus 0 squared minus 9 over 0, or 9 minus 9 over 0, which is 0 over 0. So again, this is an indeterminate form, so we have some algebra to do. Alright, so one thing we could do is we can go ahead and expand this. So we could go ahead and FOIL it out. So if we wanted to FOIL it out, we'll have 3 plus h times 3 plus h. Don't know why I drew that. Which is the same thing as if we FOIL it. 9 plus 3h plus 3h plus h squared. And so when we go ahead and try to do this, we have the same thing as the limit as h approaches 0 of 9 plus 6h plus h squared minus 9 over h. So notice that those 9's will actually go ahead and cancel. So once those 9's cancel, we'll get the limit as h approaches 0 of 6h plus h squared over h. And we're at this point, what we can do is we can factor an h out of the numerator. And so now we have the limit as h approaches 0 of h times 6 plus h over h. And now these h's cancel and we're left with a 1 in the denominator. Very important. When you cancel these, 0 does not show up. I only mention it because I've only done it 1,000 times myself. So make sure when you cancel, you're only left with a 1 in the denominator. And so now we get the limit as h approaches 0 of 6 plus h. And now when we plug in, we'll get a very easy 6 plus 0, which is just 6. So that'll be our first of these three limits. For our second limit, we're going to go ahead and try to employ a little bit of a different technique. So again, we should plug in first to make sure that we end up getting an indeterminate form. And so when we do this, we'll get the square root of 0 squared plus 9 minus 3 over 0 squared, or just the square root of 9 minus 3 over 0, which is 0 over 0. So this tells us to do some algebra. And typically, when we see a square root, what we'll do is we'll do something called multiply by the conjugate. So if you see a square root, try multiplying by the conjugate. And so if you're not familiar with the term conjugate, essentially what you'll be doing is we'll be taking this term up here, this square root of t squared plus 9 minus 3, and we'll be multiplying by the same thing, except instead of a minus 3, we'll do plus 3. Now, we can't go ahead and just start multiplying by numbers willy-nilly, so what we'll do is we'll multiply by this conjugate in the numerator and the denominator. So I'll write the conjugate in red so we can see kind of what that looks like. So now we'll have the limit of the square root of t squared minus 9, plus 9, minus 3 over t squared, and this limit is as t goes to 0, and we'll multiply it. And again, parentheses will be important here for this multiplication, times the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. So again, this is essentially multiplying by a 1. And when you do this multiplication, what you'll get is you'll get the inner and outer terms to cancel out for you. So just to see what we mean by that, when we FOIL in the numerator, we should get, when we multiply the square root of t squared plus 9 times the square root of t squared plus 9, we will get t squared plus 9. And then we'll multiply the outer, so we'll get 3 times t square root of t squared plus 9. Plus negative 3 times the square root of t squared plus 9, so minus 3 square root of t squared plus 9. And then we'll multiply the last two terms together and get negative 9. So negative 3 times 3 will be negative 9. And so that's in the numerator. But so we had our first term, our outer, our inner, and our last term. And so these outer and inner terms, when we pick our conjugate to be this, these are going to cancel out for us by doing this and picking the correct conjugate. And so this, of course, will then be divided by t squared times the square root of t squared plus 9 plus 3. And so when we do this, the 9's will cancel, 9 minus 9, and the 3 square root of t squared plus 9s will cancel. And we'll be left with the limit as t approaches 0 of t squared over t squared times square root of t squared plus 9 plus 3. And so now the t squareds will get canceled. And we'll have the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. And so plugging in now, we'll get 1 over the square root of 9 plus 3, or just 1 over 6. And so that'll be the second of our limits. Alright, so now we've got one more to go through. And so if we want the limit as x approaches 3 of 1 over x minus 1 over 3 divided by x minus 3, then what we can do is if we plug in the 3's, we'll end up with our indeterminate form of 0 over 0. Now when you've got these weird fractions, what you can do is you can try to find a common denominator. So, strange fractions. Usually this is fractions with more fractions. Find a common denominator. So, if we're looking at 1 over x and 1 over 3, our common denominator will be 3x. So we can't just multiply by 3x, we have to go ahead and multiply by 3x divided by 3x. So what we'll do is we'll have the limit as x approaches 3 of 1 over x minus 1 over 3. Again, parentheses are going to get real important. Divided by x minus 3, and we'll multiply it by 3x over 3x. So again, by doing this, we're really multiplying by a 1, but this should allow us to get some things to cancel here. And so, again, we'll rewrite our limit. This is honestly the most annoying part about the whole thing, is having to write limit as x approaches 3 every time. Well, if we multiply 3x times 1 over x, we'll be left with 3 minus, and then if we're left with 3x times 1 over 3, we'll be left with x, divided by x minus 3 times 3x. Okay, so what you might notice is that x minus 3 and 3 minus x are almost the same thing, which would let us cancel them, except for the fact that they're reverse, so they're backwards. So what we can do is we can pull a negative 1 out of this, and we'll get the limit as x approaches 3 of negative 1 times x minus 3, which you can verify by multiplying back through, will be the same thing as 3 minus x, divided by x minus 3 times 3x. So again, these x minus 3's now get to cancel, and by canceling these two, we'll be left with the limit as x approaches 3 of negative 1 over 3x. And so by going ahead and now plugging that in, we'll just get negative 1 over 3 times 3, which will be negative 1 over 9. So these just are going to highlight for us some of the very common techniques we will have when we're trying to go ahead and evaluate our limits in an algebraic sense. Alright, we're almost halfway through. Alright, so let's say we wanted to go ahead and try to evaluate a piecewise limit. So what we'll do is the first one we'll look at is f of x equals the absolute value of x. Now you might remember the absolute value of x, but just in case you don't, it's a piecewise function that says your value for the function, so the y value will be x when x is greater than or equal to 0, and negative x when x is less than 0. And so it looks something like this. And so if we want to evaluate the limit as x approaches 0 of this function, what we'll want to do is we'll want to go ahead and verify that on the different pieces we're going to the same place. So we want to verify that the limit from the left is the same as the limit from the right. And it should be, but we'll need to find out. So if we look at the limit as x approaches 0 from the left of the absolute value of x, then if we're looking at the left, so we're looking at values below 0, so less than 0, we're actually looking at the function negative x. So we'll really have the limit as x approaches 0 from the left of negative x. And so here, we can just go ahead and plug in our x, and we'll see that this ends up being 0. If we wanted to look at the limit as x approaches 0 from the right of the absolute value of x, because we're on the right-hand side of 0, and we're greater than 0, so we're on this side, we'll be looking at just x being how we define the absolute value of x. So we have the limit as x approaches 0 from the right of x, and again, this will just be a simple substitution in of 0. And so your limit on the left and your limit on the right exist, and so this tells you then that the limit overall as x approaches 0 of the absolute value of x equals 0. So that one's kind of straightforward. The next one might be a little bit trickier. So now we want to determine for this function, which is piecewise as well, if the limit as x approaches 4 of f of x exists. So what we'll do is we'll have to look at the limit on the left and the limit on the right. So the left will be our x values below, and the right will be our x values above that we'll use for our definition. So when we're looking at the limit as x approaches 4 from the left of f of x, what we're really looking at is the limit as x approaches 4 from the left of 8 minus 2x. And so at this point we should be able to go ahead and just substitute in our 4, because this function is one that is a polynomial. And so we'll get 8 minus 2 times 4, which will be 0. Next we'll look at the limit as x approaches 4 from the right of f of x. And so again, if we're looking at x values that are above 4, we're looking at this square root of x minus 4. So we'll be looking at the limit as x goes to 4 from the right of the square root of x minus 4. And here we're again allowed to just plug in. So we have the square root of 4 minus 4, which is the square root of 0, which is just 0. So then, because the left and the right limits match, our overall limit as x approaches 4 of f of x will equal 0. And so let's graph this really quickly just so we can have some practice with graphing. If we're looking at the function 8 minus 2x when we're to the left of 4, we'll be looking at a point, the y-intercept is 8, so 1, 2, 3, 4, 5, 6, 7, 8. And when we look for our x-intercept, that will be, as we've said, when x is 4, y will be 0. So we'll be looking here. And so all we have to do is connect these 2 points. It's probably not the best edge to do that with, but we'll make do. Now, meanwhile, we've got the square root of x minus 4 as our right piece. And what we can recognize from our conversations about how graphs get shifted is that this shifts the square root of x graph to the right 4 units. And so we start off here, we'll end up with this point, we'll end up with this point a little bit later, and we will keep on going. So there's our square root function. All right, a few more examples. So now that we've seen some of these limit laws, and we've gotten to see some of our tips and tricks, now will probably be a better time for you to take a moment and try to evaluate the 3 limits on this page. So I recommend going back to examples 7, 8, and 9 before trying these to make sure that you can kind of remember the tips and tricks that we'll use to solve these problems. And then pause the video, and when you're ready to see the answers, come back. Alright, so with this first limit, we're going to go ahead and try to plug in -3 directly. And when we do, we'll get -3 squared plus 3 times -3 all over -3 squared minus -3 minus 12. And so that'll be 9 minus 9 over 9 plus 3 minus 12, which will be 0 over 0. So again, we get an indeterminate form, which means we need to go ahead and do some things to try to help ourselves out. What I'd recommend here doing is factoring the numerator and the denominator. So you don't need to necessarily just pull out an x, although you can for one of these. You sometimes might need to be able to factor out the polynomial in a different way. So this is going to be the same as the limit as x approaches -3 of x over x plus 3. So this will be a way to factor the numerator. And the denominator, we want to go ahead and figure out how we can factor this polynomial. So remember, when you're looking at squares, what you want to do is you want to find 2 things that can multiply to this number and add to this number. So because this sign is negative for 12, what we know is that one of these is positive and one of these is negative. And because this sign is negative for the x, what we'll know is that the bigger of the 2 numbers has to be negative. So let's think about it. What can we multiply to get to 12? 1 and 12. Okay, well, is 1 minus 12 -1? Not quite. We can do 2 and 6, so is 2 minus 6 -1? Again, not quite. We could try 3 and 4. So is 3 minus 4 -1? It is. So we'll have x plus 3 and x minus 4. And to be fair, we should have been able to kind of get a little bit of a clue that this might be what we needed to do to get the x plus 3 factor, because we're going to want something to cancel. So since we saw an x plus 3 up here, we can kind of use that as a jumping off point if we're trying to kind of cheat a little bit and figure out a good way to factor this polynomial. So these x plus 3's will cancel, and we'll get the limit as x approaches -3 of x over x minus 4. And at this point, we've done enough work that we can go ahead and just substitute in. So we'll have -3 over -3 minus 4. And what we'll end up with is a positive 3 over 7. All right, so 1 down. So let's go ahead then and look at the next one. So if we want to go ahead and take a look at plugging directly into this limit, we'll end up with 1/5 minus 1/5 over 5 minus 5, which is 0 over 0. And so again, we had talked about if we have something where we've got some weird fractions within our fractions, we want to find a common denominator for these two that we can multiply everything by to try to make some headway. So let's do that. We'll have the limit as t approaches 5 of 1 over 5 minus 1 over t divided by t minus 5 times 5t over 5t. And so if we multiply 1/5 times 5t, we'll get t. If we multiply 5t times negative 1 over t, we'll get minus 5 divided by t minus 5 times 5t. And so now these t minus 5's cancel, and we'll get the limit as t approaches 5 of 1 over 5t, which will just be 1 over 5 times 5, or 1 over 25. Alright, so that's 2 down. For the last one, if we go ahead and try to plug in 2, this one might be a little tricky to see, but trying to plug in 2 will get us the square root of 8 plus 1 minus 3 over 2 minus 2, and so that'll be the square root of 9 minus 3 over 0, or 0 over 0. And so again, because we have this square root followed by a term, the thing that'll help us out is to multiply by the conjugate. And so remember, if our conjugate is, if we're trying to find the conjugate for a square root minus a term, we'll do the square root plus that term. And then we have to multiply the numerator and the denominator by that same thing. So we'll have the limit as u approaches 2 of the square root of 4u plus 1 minus 3 over u minus 2. And using our conjugate will be square root of 4u plus 1 plus 3 and so in the denominator we won't mess with anything too much yet. In the numerator we'll get the square root of 4u plus 1 times the square root of 4u plus 1, so we'll get 4u plus 1. And then the outside terms will be plus 3 square root of 4u plus 1. And then the inside terms will be minus 3 square root of 4u plus 1. And then the last terms will be negative 9. And so again, this will cancel with this. And in the denominator, we will end up with u minus 2 over, or times the square root of 4u plus 1 plus 3. And so by going ahead and combining some terms here, I'm going to bring this over to the other side of the page. We'll get the limit as u approaches 2 of 4u minus 8 over u minus 2 times the square root of 4u plus 1 plus 3. Now what you'll notice is that we still have, if we still try to plug in this 2, we'll end up getting 0 over 0. But what you might not notice is that if you look at this 4u minus 8, we actually can pull out a 4 to be able to reduce this further. So this will be 4 times u minus 2, and now we can try to get the u minus 2's to cancel. And so now they do, and we're left with the limit as u approaches 2 of 4 over the square root of 4u plus 1 plus 3. And so this will be 4 over 8 plus 1 square root plus 3. And so this will be 4 over 6, or just 2 over 3. All right, so we've got yet another one of these limits down. On this next page, we have a series of 5 exercises involving this piecewise function. So we want to know our limits on the left right of x equals 1, and then at 1. And then I want to know what the limits are for these as well. So again, take a moment to try to find all 5 of the asked for limits, and then come back to the video. Alright, so for the first one, if we're looking to the left of 1, we're looking at for x when x is less than 1. So this is going to be the limit as x approaches 1 from the left of x squared plus 1. And so here we can go ahead and just plug in our values. So we get 1 squared plus 1, or just 2. For our next limit, we're looking at g from the right of 1, but as close to 1 as we can. So we'll be looking at this next piece of x minus 2 quantity squared. So this is then the limit as x approaches 1 from the right of x minus 2 quantity squared. And so this will be 1 minus 2 squared, or just 1. Well, that means that if we want to find the limit overall as x approaches 1 of g of x, since these two don't agree, this does not exist. So we would need them to match. Okay, the next thing we want is the limit as x approaches 4 of g of x. And so notice here that 4 isn't exactly a point that's kind of on the boundary of things, but we need to know which part of this function we're looking at. So if x is approaching 4, we're looking at x values greater than 3. So we have then the limit as x approaches 4 of 2x minus 5. And so here we can just directly plug in. And so we'll get 2 times 4 minus 5, or just 3. And then our last limit on this page asks us to go ahead and find the limit as x approaches 3 of g of x. And if you'll notice, 3 is one of our points where we have 2 different definitions for g of x, whether on the left or on the right. So when we look at the limit as x approaches 3 from the left of g of x, this is the limit as x approaches 3 from the left of x minus 2 squared. So it'll be this part. So plugging it in, we'll get 3 minus 2 squared, or just 1. Okay, now we need to check our limit on the right. So limit as x approaches 3 from the right of g of x. And so our definition for g of x when we're to the right of 3 is 2x minus 5. So then we're looking at the limit as x approaches 3 from the right of 2x minus 5. And so that's 2 times 3 minus 5, or just 1. So, since the limit from the left and the limit from the right agree, the overall limit as x approaches 3 of our piecewise function g of x is just 1. Alright, so we have one more idea to talk about involving limits. And this will be kind of one more tool for us to try to compute limits exactly. So, we know that if we want to go ahead and have something that is referred to as a continuous function, which we'll talk about what that means, we can use our direct substitution method. So we can just plug in the thing that we are taking the limit to. We also know that there are some times where we'll have to do some algebra in order to simplify the function to use direct substitution. So, in other words, we could have things where we need to go ahead and find those common denominators, go ahead and use the conjugate, factor out in some way. The last way is to use something called the squeeze theorem. Alright, so the squeeze theorem says that assume that x is not equal to c for some interval contained in some open interval containing c, and we know that we've got a lower function and an upper function that are both bounding some f of x. So no, basically what we're saying is we've got some function and there is a function below it that's always below it or equal to it, and there's a function above it that's always above it or equal to it. And we know that the limit as x approaches c for both the lower and the upper functions are the same, and there's some limit. Then what we're then saying is that the limit as x approaches c of this middle function here exists, and it has to be the same as this L. So let's kind of break down what's going on with the squeeze theorem. So first thing we're doing is we're saying we have some sort of bounds for f of x. So we have some upper function u of x such that f of x is always less than or equal to u of x, and some lower function L of x where f of x is always greater than or equal to L of x. So something bigger and something smaller. What we know is that our limit as x approaches c for the lower thing is equal to L, and our limit as x approaches c for the lower thing is also L. So essentially think of us having some sort of upper function, so this upper dashed line is u of x, and this lower dashed line is L of x, and this wavy function here is our f of x. So maybe f of x is some sort of weird thing like sine or cosine, and it's got some weird algebraic stuff going on inside of it, and we don't know exactly what the limit should be at this particular point here in the middle, but we do know that f of x is always less than or equal to u of x, and we know it's always greater than or equal to L of x, and they both meet at this point. Well, what that means is that f of x is going to be forced, because it's kind of squeezed in there, to also have that limit at that point. So the limit then, as x approaches c of f of x, will be equal to L. So note here that if the limit as x approaches c of u of x is not the same as the limit as x approaches c of L of x, then the squeeze theorem does not apply. So it tells us nothing at that point. So we need to make sure that those limits for the lower and upper function end up being the same. Otherwise, the squeeze theorem won't be our go-to tool. So we've got two examples for trying to use the squeeze theorem. So first, say that we're trying to evaluate the limit as x approaches -4 of some g of x, and we know that 9 is always less than or equal to g of x, and x plus 13 is always greater than or equal to g of x for where we're looking at. So first, we have our bounds that are given for g of x. So we've got our upper function is x plus 13, and our lower function is the constant function 9. Next two steps are to find those limits as x approaches -4 of both of these. So for the upper function, that's the limit as x approaches -4 of x plus 13, which is just negative 4 plus 13, which is 9. And for our lower function, that's the limit as x approaches negative 4 of 9, which is 9. So the squeeze theorem says the limit of as x approaches negative 4 of 9 has to be less than or equal to the limit as x approaches negative 4 of g of x, which is less than or equal to the limit as x approaches negative 4 of x plus 13, which tells us then that 9 is less than or equal to the limit as x approaches negative 4 of g of x, which is less than or equal to 9. And so if g of x's limit is both less than or equal to 9 and greater than or equal to 9, then that tells us then that the limit as x approaches negative 4 of g of x has to be equal to 9. So there we didn't need to know what the function was, we just had some boundaries for it, and that allowed us to go ahead and compute what it is that limit would be. So that was kind of a little bit more trivialized example. Let's look at something a little more concrete. So say we wanted to look and evaluate the limit as x approaches 0 of x squared times the sine of 3 pi over x. So note that this then becomes 0 times the sine of 3 pi over 0, which is something that we're not quite sure what to do with. So here, algebra won't save us. Oh no, our algebra is useless, it's finally failed. So now we'll have to use the squeeze theorem. Okay, so if we want to use the squeeze theorem, what we'll want to do is we'll want to go ahead and try to find some easy boundaries to use. So step 1 is to find bounds. Now, if we look at this function, we've got an x squared portion and we've got a sine portion. Now, one thing we should know is that the values for sine of x on its own have to be between negative 1 and 1. So we know that negative 1 is less than or equal to the sine of 3 pi over x, which is less than or equal to 1. So we'll start with this idea. And typically for these sines and cosines, we'll start with this idea that their values on their own can't go above or below, they can't go below negative 1 or above 1. Now note that this is not the function we have. This is the function we have. So now what we can do is we can multiply all sides of this by x squared. And note that x squared is positive, so we don't have to worry, or at least it's non-negative, so we don't have to worry about changing the direction of any of these at all. So if we have this as our implication, then negative x squared will be less than or equal to x squared sine of 3 pi over x, which is less than or equal to a positive x squared. So now, this will be our L of x, and this will be our U of x. So then steps 2 and 3 will be to find those limits for those lower and upper bounds. So we want the limit as x approaches 0 of u of x, which is just the limit as x approaches 0 of x squared, which is 0. And we want the limit as x approaches 0 of L of x, which is the limit as x approaches 0 of negative x squared, which again is 0. So now Because we have a lower and upper function whose limits, as x approaches 0, both go to 0, this tells us then that by the squeeze theorem, the limit as x approaches 0 of x squared sine of 3 pi over x equals 0. So off here over to the left, you can see that we've got a nice picture that kind of shows off what this looks like. Note though that we won't always have this picture to go off of, so we'll have to do a little bit of work on our own to find those lower and upper bounds. Alright, so now we've got a bunch of tools that are going to be used for finding limits. Limits are very important because they're kind of the theoretical backbone for helping us find these rates of change a little more easily and in a more systematic way. And they'll be used for a lot of things going throughout the rest of this course. In the next section, we'll be talking about the idea of continuous functions, which are ones that we can then go ahead and use that direct substitution method on immediately.